group 15 hydrides. Hydrides of group 15. Group 15 elements forms hydrides of this type XH3. The central atom is H, that is nitrogen, phosphorus, arsenic or antimony. And if you look at this, the central atom X undergoes sp3 hybridization. So we have this NH3, PH3, ASH3, SBH3, BiH3. Their name, this is ammonia, phosphine, arsine, stibine and bismuthine. Now the hydrides of this group, if you look at this, the size of central atom increases down the group, where the size of hydride ion is very small, so size difference increases. As the size difference between the central atom and hydrogen increases, the bond length will increase. As the bond length increases, bond stability will decrease. As the bond stability decreases, bond energy will also decrease. So nitrogen XH bond length increases. As the bond length increases, bond energy of this XH also decreases. The strongest bond is formed by nitrogen hydrogen. As the bond energy decreases or the bond length increases, bond stability also decreases. Now, as the stability of these hydrides decreases due to the difference in size, larger difference in size, these hydrides also shows reducing character. So again the reducing character increases. So all this due to the larger difference in size. So because of this larger difference in size, stability down the group decreases. As stability decreases, bond length increases, bond energy decreases, or the reducing character increases. Ammonia does not show reducing, but the rest of this hydride shows reducing character. Now, these hydrides also shows poisonous nature. So poisonous nature again increases down the group, and these hydrides of this group 15 contains a lone pair of electron. So the central atom contains a lone pair. Due to the presence of lone pair, this hydride shows the basic property, but the basic property decreases down the group. Now if you look at this, nitrogen is the most electronegative, bismuth is the least electronegative. So in terms of electronegativity, this bismuth should be having the most basic property and the nitrogen hydride should be having the least basic property. But here the basic property is explained based on electron density. As the size increases, electron density decreases. As the electron density decreases, tendency to donate electron also decreases. It is due to decrease in electron density on increasing size, the basic character decreases. So the smallest size, maximum electron density, maximum donor property. So this is the basic character of these hydrides. So you have to follow this basic character. So ammonia is the strongest base and this methyl is the least basic. The reason is due to this electron density decreases down the groove with increase in size. Now coming to solubility or the melting point. Melting point of this. Now as the size increases, the intermolecular attractive force also increases. As the intermolecular attractive force increases, the melting point will also increase. So melting point, boiling point we'll discuss here. So PH3, then AHH3, then we have NH3, HBH3, then BiH3. Now look at this. This is due to hydrogen bond. But accepting this NH3, moving from phosphine to bismuthine, size increases, intermolecular attractive force increases, so the boiling point will increase or the melting point will also increase. The exceptional value is for this ammonia due to hydrogen bond. But when we compare the bond strength or bond angle, in case of ammonia, the bond angle is 107, PH3 approximately 93.5, this is 91.5 and this is approximately 90. So if you look at this bond angle of this hydrides decreases down the groove. If you look at this, the last four hydrides of last four, phosphorus, arsenic, antimony, bismuth, the bond angle is approximately equals to 90 degree. As the bond angle is approximately 90 degree or which is very close to 90 degree, the concept of hybridization does not take place. So hybridization is less prominent, and in fact pure p orbitals are used for bonding. Now since pure p orbitals are used for bonding and all the three p orbitals are perpendicular to each other, so the bond angle is approximately 90 degree, that is perpendicular. Now since pure p orbitals are used, so again the bond becomes weaker bond and the bond length increases or the bond stability decreases. Now look at this. We are saying this is undergoing sp3 hybridization, so bond angle should be 109, but due to this lone pair, we have, look at this. So we have a lone pair, so this is due to lone pair bond pair repulsion. The bond angle is less than tetrahedral angle of 109. So in case of ammonia, hybridization is prominent, and because of this lone pair, the bond angle is slightly less than tetrahedral angle of 109. In the rest of these hydrides, bond angle is very close to 90 degrees. So this indicates the use of pure p orbitals for bonding between the central atom and the hydrogen. So the bonds are weaker, and bonds are weaker means the stability of the hydrides are less. So this is all about hydrides of group 15. Now coming to halides. Halides of group 15. Group 15 elements forms two types of halides. Forms two series of halides, that is EX3 and EX5, that is trihalide, and this is pentahalides. So coming to EX3, this is the central atom. So central atom undergoes sp3, and this contains 3 bond pairs and 1 lone pair. So due to the presence of this lone pair, this EX3, this is pyramidal, and the bond angle is less than 109. That is lone pair bond pair repulsion. So if you look at this, we have this E X X, we have a lone pair. So this bond angle, this is less than 10 due to this bond pair lone pair repulsion. Now all halides of this group 15 except NCl3, NBr3, Ni3 are stable. So the instability of these three halides of nitrogen, that is NCl3, NBr3 or Ni3, this is due to less polar or less electronegativity difference. Because of this, these are less stable. And if you look at this, all these halides contains a lone pair. So because of this lone pair, these act as a basic in nature. So when we compare the basic character, look at this NF3, NCl3, NBr3 or Ni3, each central atom contains a lone pair, so this can act as a base. But moving down the group from fluorine to iodine, electron negativity decreases. So fluorine being the most electronegative, electron density on nitrogen is the least. Iodine being the least electronegative, electron density on nitrogen is the more. So as the electron density increases, basic character also increase. So this is due to increase in electron density due to decrease in electronegativity from fluorine to iodine. But if you look at this bond angle, the bond angle also increases from fluorine to bromine to iodine, because size increases. As the size increases, steric strain also increases. Due to increase in size, steric hindrance increases. So as the steric hindrance increases, the bond angle also increases. So this is X3 series, that is trihalides. These also forms pentahalides. Now coming to pentahalides, EX5, nitrogen does not form pentahalides due to absence of d orbital. So nitrogen cannot undergo expansion of octet due to absence of d orbital. whereas rest of the elements due to the presence of vacant d orbital can undergo expansion of octet. So this pentahalide is formed by all elements except nitrogen. As I told you, nitrogen does not have d orbital, so this cannot undergo expansion of octet. So if you look at this is the central atom. The central atom is undergoing sp3d, that is trigonal bipyramidal structure. So we have look at this. It is central atom. We have this X, 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 X. These two bond, this is known as axial bond, and these three bond, this is known as equatorial bond. Now EX axial bond length is greater than EX equatorial. Bond stability, equatorial is more stable. Reactivity, axial is more reactive than equatorial. So this is because of this 90-degree repulsion. So we have looked at this. These and this undergoes 90-degree repulsion. Because of this 90-degree repulsion, to minimize the repulsion, this bond is slightly increased. As the bond length increases, bond strength decreases, or bond stability decreases, or the reactivity increases. So means in case of this, we have two types of bond, axial bond and equatorial bond. One of the most prominent pentahalide that we find often used in chemistry is PCl5, phosphorus pentachloride. These exist in molecular form in gases only. In solid, these exist in ionic form. In ionic form, and that ionic form, look at this. This exists in PCl4 plus and PCl6 minus. So this phosphorus, this is sp3 tetrahedral, and this phosphorus is in sp3d2 or octahedral. So we have two phosphorus in the solid state. One is in tetrahedral form, the other one is in octahedral form, and this finds application in organic chemical reactions. So these are two different halides of group 15. So group 15 shows two types of halide, trihalide and pentahalide. So we have discussed this. EX5 pentahalides, all these pentahalides shows Lewis acidic behavior, whereas trihalides were basic, while EX5, the pentahalides are Lewis acid due to the presence of vacant d orbital. So this vacant d orbital can accept electron pair, and electron pair acceptors are known as Lewis acid. So in many of these reaction, organic chemical reaction, we use PCl5 as a Lewis acid. So this is the reason why pentahalides are acidic, because of the presence of vacant d orbital. They show tendency to accept electrons. Now coming to oxo acids, of this group 15, nitrogen shows two types of oxo acids, HNO2 and HNO3. Nitrogen plus 3, nitrogen plus 5. This is nitrous acid. and this is nitric acid. So we have this nitric acid. Let me give you just some of the basic properties of this. Preparation, Oswald method. So we have this. First we start from ammonia. Ammonia on combustion gives you NO, and second this NO further reacts with oxygen to give you NO2, and in the third step this NO2 reacts with water when this gives you nitric acid, and we often use the term fuming nitric acid, that is a mixture of nitric acid and NO2. NO2 is brown, so the color of this is brown color. So this is how we prepare nitric acid in laboratory by Oswald method. Now we say this is acid, so this will show all the properties of acid. Along with this, one of the most important property of this acid is oxidizing agent. So nitric acid is a very good oxidizing agent. So we have look at this HNO3 dilute. This gives you NO plus 3 active oxygen is formed. So due to the formation of these 3 active oxygen plus we will have this H2O. So this is responsible for oxidizing property. It's a very good oxidizing agent. So whenever we use nitric acid dilute, the final product will be NO. But if we use this nitric acid concentrated, then this gives you NO2 and 1 active oxygen is formed. So when nitric acid is used as an oxidizing agent, the product will be NO2. NO is formed when we use dilute nitric acid as an oxidizing agent. So this being a very strong oxidizing agent, this can oxidize even the non-metals. So sulfur, when this reacts with concentrated, this gives you sulfuric acid plus water will form. Phosphorus, when this reacts with nitric acid, this is converted into phosphoric acid plus NO. Carbon, when this is reacted with nitric acid, this is converted into carbonic acid. So this being a very strong oxidizing agent, this oxidizes non-metals. Even this iodine can be oxidized with nitric acid to give you HiO3. So in all these cases we have this. If this can oxidize non-metals, the metals can be easily oxidized. So even this sulfur dioxide can be oxidized by this to give you sulfuric acid plus NO. We can have this Ki reacts with nitric acid, when this gives you I2, and this NO is formed. So I minus is oxidized to zero oxidation state. Similarly, look at this. Some metals like iron, when react with nitric acid concentrated, this gives you plus NO is formed. So this is concentrated, so this will give NO2. to copper nitric acid. This gives you cupric nitrate plus N2. Even look at this, mercury reacts with nitric acid when this gives you mercuric nitrate plus NO2. Even this Mg reacts with nitric acid concentrated to give you magnesium nitrate plus NO2. So this being a very strong oxidizing agent can oxidize non-metals, even the ions can be oxidized, and the metals can also be easily oxidized. But there are certain noble metals like gold, silver, platinum. So these elements are known as noble metal because their reactivity is very poor, like gold, platinum, iridium, rhodium, etc. Gold, rhodium, iridium, platinum. These are noble metals. No reaction with nitric acid, but dissolves in aqua-regia. So what is aqua-regia and how does this react with aqua-regia? Let's see. Aqua-regia is a mixture of HCl and nitric acid in 3:1 ratio. 1 part of nitric acid and 3 parts of HCl reacts to give you this aqua-regia, and this aqua-regia produces active chlorine. This active chlorine is acting as an oxidizing agent. Due to the formation of this active chlorine, this aqua-regia acts as a very strong oxidizing agent. So this gold reacts with this aqua-regia, that is active chlorine, when this gives you auric chloride, iron plus 3. Similarly, platinum, this reacts with this mixture HNO3 plus HCl. So this gives you active chlorine, when this gives you chloroplatinic acid, which is a very strong acid. Chloroplatinic acid. So this is oxidized to +4 oxidation states. So aqua-regia, these noble metals does not reveal normal acids, but this dissolves in aqua-regia, and aqua-regia gives you active oxide chlorine, and this active chlorine is acting as an oxidizing agent. This is how this reacts with aqua-regia. So these were some of the properties of the oxoacids of nitrogen. Now coming to oxoacids of phosphorus. Oxoacids of phosphorus. For this I'll give you a tabular form. So we have HPO starting from this. We have 3,1,2 series, 3,1,3 series, 3,1,4. So this is H3PO2, phosphorus in +1 oxidation state. This is H3PO3, phosphorus in +3 oxidation state. H3PO4, phosphorus in +5 oxidation state. This acid is known as orthophosphorus. This is phosphorus acid. This is phosphoric acid or simply orthophosphoric If you look at the structure, in all this phosphoric acid there is a P double bond O, then the rest we can assume as it is. So we have this. This contains only one ionizable H plus ion, so N factor, that is 1. Now due to the presence of this direct phosphorus hydrogen bond, this shows this reducing property. So this H3PO2 is a reducing due to the presence of this hydrogen directly bonded to phosphorus. Phosphorus acid, so as we have this P double bond O, we have POH and one P hydrogen. So this is ionizable, so N factor is 2, and this again shows reducing due to the presence of phosphorus hydrogen. This is phosphoric acid structure, P double bond O, OH, OH, OH. All these 3 hydrogen is ionizable, so N factor is 3. So this forms 3 series of salts. Then we have four to 6 series, that is H4 P2 O6. If you look at the structure, P this is the structure of H4P2O6. This is known as hypophosphoric acid. Hypophosphoric acid, oxidation state +4. This is structure. Look at this, N factor is 4. There are 4 ionizable hydrogen. Then we have 427 H4 P2O7. Compound is known as pyrophosphoric acid. Structure EOP, double bond O, double bond O, OH, 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 OH. This is oxidation state is +5. Both phosphorus is in +5 oxidation state. And the first one is 113, that is HPO3, that is metaphosphoric. Oxidation state is +5. So this exists in cyclic as well as polymeric forms. So these are oxoacids of phosphorus. So it's very easy to remember this oxoacids of phosphorus. So for this oxoacids of phosphorus, we have to remember the oxidation state, structure, why they are reducing, are they reducing or non-reducing, what is the cause of reducing, then how many phosphorus double bond oxygen or phosphorus O bond is present, along with their oxidation state, and the name should also be remembered. So these are the oxoacids of nitrogen and the phosphorus of this group 15 elements. So with this we come to the conclusion of group 15, some of the important compounds of group 15. So I'll take some more examples of ammonia as an important compound, because ammonia is also a very important compound of group 15. So I shall rub this. So one of the important compounds of this group 15 is NH3, ammonia. First look at this preparation of this ammonia. That is known as Haber's process. Haber's process. So that is, we have nitrogen plus hydrogen gas in presence of iron as a catalyst, molybdenum taking as an promoter. We have this NH3 gas. So this is a reversible process. For this process, delta H is negative, so the reaction is exothermic, so temperature should be at low temperature and high pressure conditions should be applied so that the reaction shifts in the forward direction. Coming to properties, as we have shown you, this is an basic. So this reacts with acids to give you salt, ammonium chloride. This reacts with sulfuric acid to give you ammonium sulfate. This reacts with perchloric acid to give you ammonium perchlorate, etc. So this solves as basic property of this ammonia. So aqueous solution, look at this. Ammonia dissolves in water when this gives you ammonium hydroxide. So this is a weak base. So ammonia is not a strong base, but this is a weak base. So aqueous solution, this is used for hydrolysis. So look at this, AlCl3, when this reacts with ammonia aqueous, this gives you hydroxide plus HCl, that is FeCl3. We react with aqueous ammonia, that is hydrolysis reaction, FeOH3 plus HCl, even we can, that is copper chloride, ammonia aqueous, so this gives you copper hydroxide plus HCl, etc. Along with this is also involved in complex formation, complexation reactions, that is copper sulfate aqueous plus ammonia aqueous. So this gives you tetraamine copper 2 sulfate so we have this complex. Similarly, we can take this FeSO4 plus ammonia taken in excess quantity, so we have that is AgCl plus ammonia aqueous, AgNH3 whole twice Cl. So this is how complexation reaction takes place. So this ammonia can also use for hydrolysis as well as for complexation reaction. We can take this zinc sulfate reacts with ammonia in excess quantity when this gives you tetraamine zinc sulfate. So all these are known as the complex. So this is complexation reactions of ammonia. Now let me give you some taste for ammonia. Hydrolysis reaction. Taste for ammonia. So chemical test with Nessler's reagent. Nessler's reagent. So ammonia reacts with Nessler's reagent K2HgI4. This complex is known as Nessler's reagent K2HgIO4, and this gives you NH2HgO SGI, that is brown precipitate. So ammonia, when it reacts with Nessler's reagent, Nessler's reagent is, this is complex is known as Nessler's reagent. When this gives you the brown precipitate with this composition, so this gives you the confirmatory test for Nessler's reagent. And the next is with chloroplatinic acid. Chloroplatinic acid test. So ammonia reacts with platinic acid PtCl6 when this gives you yellow precipitate. So the hydrogen of platinic acid is being replaced by ammonium ion and this gives you yellow precipitate. So this is specific test for ammonia. Apart from this, we can also have when ammonia vapor gas, so we take a glass rod, we dip this glass rod in HCl solution and is placed in the mouth of a solution containing ammonia. This gives you white color fumes, so ammonium chloride is formed. So formation of white fumes when this rod dipped in HCl is placed in the mouth of aqueous ammonia is due to the formation of ammonium chloride. So we can also have a litmus test, we can have a smell, the choking smell of this ammonia. So this is the important compound of ammonia and its taste for ammonia, means some of the properties of ammonia. So this is a brief idea about group 15 elements, their basic properties and their common compounds. So I hope with this will conclude this group 15 elements. Meet you again in next class. Thank you.